Okay, so let me say a couple of things. First of all, Math Club, today, 5 o'clock, we got a visitor, Michael Joseph from Dalton State. He's finished work with Macaulay. Anyway, he's going to talk about catalog numbers in the Math Club. He's also going to be doing the ADN seminar today. So I encourage you all to do that too if you've got a chance. It's 11:15 and one of these is in one of the four. The math in is tomorrow. So if you're helping out, great. If you want to drop in to help out, great. And the math in isn't just calculus. So if you're working on your final or getting caught up on your homeworks, you can come by and ask me. I'll be there all day and use class 8 math in. Do your assessment if you haven't already. I think most of the people in here you have done it, but just make sure that you do that. Do the evaluations. I've got them closing like I think next Friday, but you know, if everybody does one of these, that's another homework for you. And next week my office hours will be on demand because I've got some family things to do. I'll try to remember to email out my cell phone too as well. But you need, yes.
But when you say do assessment, that was the thing you're talking about, go to your office.
That's the one, yeah. And so and don't forget, we will have our final exam, the final class we'll have on Thursday, and kind of touch up some last minute stuff. Maybe have just kind of a fun lecture. Okay, any questions? All righty. So, welcome to the last day of sort of regular lecture for Thursday. So we've been talking about valuation domains. I'm going to give you something that we're going to use that's this little lemma that I'm going to give you, or whatever I call a proposition, is of its own independent interest, but it's actually important in showing really part of the real importance of valuation domains. Isn't it weird that we're talking about valuation domains right after Grant talked about integral closure, right? It almost seems like I've gotten off track or something like this, right? Because we know the valuation domains are integrally closed. We showed that last time, but there doesn't seem to be much of a connection yet. But there is. Let me give you the following lemma. Let's let R inside T be domains. And I and R a proper ideal. Well, proper ideal. And U a unit in T. So U is just some element that happens to be invertible in the big ring T, in the big domain T. Then I survives in either RU or R inverse. Now let me tell you what I mean by survives here, so we're clear. And we say I survives to be if IT is properly. So let me give you kind of a non. So what it means is I is a proper ideal of R if the ideal of T that is generated by I is still a proper ideal upstairs, we say that I survives. So for example, if you look at the ordinary integers, and look at the ideal generated by two, so all the even integers, that's a proper ideal. If you lift that ideal up to the quotient field Q, that does not survive, right? Because the ideal generated by two inside of Q, well, two is a unit up there, right? So it just subverts it. So it just means that the smallest ideal that contains the set I and T is still a proper ideal. So this is the big thing. If you have R inside T domains and I is proper ideal, then I must survive in either RU or RU inverse. It must remain a proper ideal and R joined with the U or U inverse. So let's go through this. Suppose not. Well, what does that mean? That means that we have the equations with AI and R and with each AI, BJ, and I. What? Yes.
So maybe this is the question. Is IT guaranteed to be an ideal?
Yeah. Sure.
Okay. And that's just a property of you take an ideal with a domain. But that's
Right, because a typical element of this will look like some alpha I Ti with alpha I and Ti and T. And if you add any two things in this form, it's still that form. And if you multiply this by T, it's just absorbed alpha Ti's, right? So yeah, it's the smallest ideal, it's the ideal generated by the set I in the bigger range. So what these equations come from is we're supposing not. That means that I doesn't survive in either of these. That means that I times RU is contains the element 1, and it means I times RU inverse contains the element 1. What does that translate to? What does a typical element of I times RU look like? It looks like so it looks like a little polynomial in U with coefficients in I. So each of these are in I, and so there must be some polynomial with coefficients in I times powers of U that equals 1. And same thing with U inverse. Right? So both of these equations have to happen. Now I'm gonna specify some things. Assume of course, you can always assume that n is greater than or equal to m. If not, just reverse the roles U and U inverse since it's a unit, and assume that we have minimality. So this is sort of the shortest equation that we can obtain. Next.
so what are you claiming is minimal? And
Yes.
so I guess I'm confused about which order we think. Like if we're saying n is greater than m, then it seems like you might have to swap the two different boundaries. Like if you're always bigger than n, then you say take n minimal, but then it might go below.
N is minimal because n is the one for U, right? So n corresponds to u, n corresponds to m corresponds to u inverse. And you can always assume that n is greater than or equal to m, because again, you can invert the roles of u and u inverse. Because whether I call this u or u inverse is immaterial, right? So you've got one of these, this is the bigger one, and assume that the bigger one is minimal. Right, so you've got two equations, one for an element, one for its inverse. Take the bigger one and assume that that n for the bigger one is minimal. Okay, so what I want to do is I want to multiply the second equation by un. Right. And rearrange this so I can obtain the following, and I'll talk us through this. 1 minus un is b1 and minus 1 plus bm un minus. Let me check this out, making sure this makes sense. So we took the second one and we multiplied it by u to the n. So that's going to give me a b0 u to the n and a 1 times u to the n. And I brought that b0 over the other side, so it's 1 minus b0 u to the n. And the rest of this is b1 u to the n minus 1, b2 u to the n minus 2, all the way up to bm u to the n minus. Everybody okay with that? I have a full fast one on you. We also get right. And now we want to substitute for 1 minus b0 u to the n. Let's see if we can figure out how we get this. Well, perfect. I can get this. Let me take the detail here. Multiply first equation by 1 minus b0. See how that works out. A0, 1 minus b0 plus 1 minus b0 on u plus 1 minus b0 a n u n equals 1 minus b0. Now, notice that I've got this 1 minus 0 un as a factor of this particular term, which is this thing right here. So doing that substitution and augmenting what I've done here, I get this equation: 1 minus b0 an this thing b1 u n minus 1 plus bm u n minus m. That's 1 minus b. And so this gives me, rearranging this a little bit. B0 plus, actually, let me write it on story over here. So at the end of the day, I get this. I'm going to bring that B0 from the other side. 1 minus B0 A0 plus 1 minus B0 A1U plus all the way up to AN B1 UN minus 1 BM UN minus M 1. Now let me make an observation about this equation. This is an equation in U, right? It's a mess, but it's equation in U. Notice B0 and A0 are in the ideal, so this coefficient's in the ideal. A1 is in the ideal, so this coefficient's in the ideal, all the way up. AN is in the ideal, so every coefficient of these are all in the ideal. Equals 1, right? So it's the same form of the equation we had here, where all the coefficients are in the ideal, equals 1, powers of U, but now the maximal power of U is n minus 1. And there you go. Because we reduce the size of this equation. So you can't have both of those equations. Cannot both be true. So I must R U or R members. Okay. Any questions? Okay. I am now going to give you two really big central theorems about why valuation domains. Right. The first one basically says, if I give you any integral domain and some proper ideal inside it, I can find a valuation over into that. So I can find a valuation domain that contains your original ring where that proper ideal still survives in that valuation ring. So, in other words, if you have any proper ideal in the ring, you can lift it up to this valuation domain where that ideal survives. And actually, the proof shows something else. It shows that there's sort of a maximality condition. Theorem. Let R be a domain with quotient with K. And I and R a proper ideal. Then there's a valuation overing of R. There exists a valuation over of R. And remember what it means to be an overring. It is just a ring that is between that domain and its quotient field. V, such that I survives. That is to say, not size n, IV is not equal. Let me give you some examples. Take the ordinary integer z, look at the ideal generated by 0, which is 0. I can think really quickly of a valuation domain that where 0 survives the quotient field. All right, so that's my easy way out on that one. Look at the ideal generated by 2, which is prime. Z localized at 2. That's valuation domain where that prime ideal survives. The ideal generated by 30. 30 is 2 times 3 times 5. I can think of 3 valuation domains where that survives. Z localized at 2, Z localized at 3, Z localized at 5. Right. But this says it in general context. Any proper ideal of R survives in some valuation over. So let's prove this. By the way, any guesses before I kind of roll out the guns here about what we're going to do? Well, these things are, in general, I gave some examples, kind of easy, just actually think on value. In some cases, you're not going to be able to do it. We're just going to be in existence. That sounds like someone's limit to me. Okay. And this is something that shows up in algebra a lot. Here's the strategy. First, we show that there is a maximal. Well, let me use this. An overview of R that is maximal with respect to the property that I survives. So what I'm going to do is so here's the first part of the strategy. I'm going to look at all the overrings of R, and I claim I can find one that is maximal with respect to the property that I survives in. So in other words, in this overring, I will be a proper ideal, but any ring that properly contains it, it blows up. It gets a unit. Right? And part 2, I bet you can already guess. Part 2 of this will be show any ring that is any overring that's maximum with respect to its property has to be evaluated. Right? And there we go. So how do we do this in the first place? Well, we consider so this is an axiom of choice. Zorn's on the thing. So what I'm going to do is I'm going to consider all pairs. RJ, IJ, J in some index set. Such that R is contained in RJ, which is contained in the closure field. So RJ is an overring. And I contained as a set in IJ, which is a proper item. So these pairs are overring and an overring of R and an ideal of this that is proper and contains the set I. That's it. So this is just kind of like an analog to the pair RI. This set is a partially ordered set under inclusion. And let me be careful about what I mean. I mean sort of double inclusion in the following sense. So we say that what do you suppose my partial ordering here is going to be? How are we going to declare that RJ, IJ is less than or equal to RJ, IJ? Right, I have taught you too well. No, we don't need the library here. Although that would totally work things, but you're going to have a problem here. Right. You're not going to be able to put the library order on it because the problem is the reason library order works is separate pieces are totally ordered, right? But here, you're not going to, RJ and RJ prime in general may not be comparable at all. So we're just going to go, yes.
And was it confused by ice and J? So you haven't said that has anything to do with R other than that it's contained with ice and J. Is that supposed to be, is the intent that ice and J equals RI or
No.
or ice and J I?
It's just any proper ideal that these eyes are set.
So I would be a valid ideal.
If it's an ideal, right? So the problem is I is an ideal of R, but it may not be an ideal as a set. It's an ideal of R, but it may not be. So, but in fact, a valid ideal will be I times RJ, as long as it's proper. All right. So yes, you. For example, one of the things could be I times RJ, as long as I times RJ is strictly contained in RJ. All right. Because this has to be for us to include a pair. This has to be an overring. This has to be an ideal of this ring that contains I as a set. Right. And so if you look at I times RJ, that's an ideal of this. So you're halfway there, but you're only allowed to include it if that's actually contained in R. If this actually blows up, if this is actually equal to R, then the pair RJI, the pair RJIJ wouldn't even be in there because it blows up in R. So we're going to do just what's called a product order, which is, it's definitely a partial order. If and only if RJ is contained in RJ prime and IJ is contained in IJ prime. So you have to have both of these conditions, right? So for example, RJ and RJ prime might be the same ring, and there might be many ideals that are contained. So there's all kinds of ways to do this. Okay. So this is our partially ordered set. We now show any chain set RJ, IJ, and some other index set has an upper bound. in the set. Okay, so it seems like these zones, one of the things are, this one's a little bit different because it's probably the first one I've done in this class where we're actually probably fair, not just one thing, but it's very similar. So anybody want to guess what's a good call for the upper bound here? Yeah, there we go. Let's call it A union. Notice that as these are unions, or as RJ is a chain, T is a ring, but domain. Let me just say no ring. Bar. That's important because actually under our partial ordering, for everything in this chain to be totally ordered, comparable, that means that all the rings are comparable and all the ideas are comparable. Also, A is closed under addition and multiplication. Would you all let me go through that? Under additions, say. Because suppose you have two elements of A, then A1 is in RJ1 and A2 is in RJ2. And we will say that RJ1 is contained in RJ2 without loss of generality, because that's a chain of rings. Therefore, A1 and minus A2 are in RJ2. So their sum, which is A1 minus A2, is in RJ2, which is contained in A. Right. The only thing left I have to worry about is it a vacuum thing, right? Does it suck? Does it be multiplied by some BT that's still in there? So let A be an A and T and T, then A is in RJ1 and T is in actually, I use my notation here. Well, I'm so sorry about this. All these R's appear to be I's. This is the ideal. It's all the same. Yeah, so I'm talking A, I'm talking about the ideals, not the rings. For the vacuum cleaner property, suppose A is in IJ1 and T is in RJ2, right? Well, this means that IJ1 is contained in RJ1. Right? And so one of two things happens. If RJ1 is contained in RJ2, then IJ1 is contained in IJ2. And therefore, T is in RJ2 and A is in RJ2 or IJ2. Because it's in the smaller one, so it's in the bigger one. So TA is in IJ2, which is contained in A. And if the inclusion is reversed, it's very similar, right? Everybody okay with that? So this is these unions, the union of T, union of A, this is an ideal of T. We've shown that. And it's maximal. What's the only thing left we got to do? So TA is maximal, but need to show it is in original set. So what do we need? We need T to be an overring of R. Check. We need A to be an ideal of T. Check. We've already checked that. We need A to contain the set I. Check. Because A is a union of a bunch of things that contain the set I. So good to go. The only thing, what's the missing piece that we need to verify? It wouldn't be proper of me to not ask that question. Needs to be a proper idea. It can't be just because it occurs to me that A might blow up and be the whole thing, and then it's not said anymore. So we need to verify that this is a proper idea. Anybody see how to do it? Yeah, absolutely. Suppose not. A, C, then 1 is in A. But A is the union of IJ and whatever it was gamma, I guess. Therefore, 1 is in IJ alpha for some J alpha in the index set. And this is contradiction. So A is proper and claim is established. So there must be an overring that is maximal with respect to the property that I survives. Now, next step. Well, let me formally write this down. So by Zorn, there exists BJ maximal element. So B is overing J and B is proper and contains I. And if B prime strictly contains B, then I B prime. So this is as big as possible where I survives. Zorn tells us that such a thing exists. And you really do need the active choice here. Some overing structures can be extremely complicated. Now we want to show that this is valuation done. Yes, evaluation. To this end, we will assume not. If not, there exists alpha and K such that neither alpha nor alpha inverse is indeed correct. So now look at B. Right. As J and B proper, J survives. And either the alpha or the alpha inverse. Right? That was the previous one we showed that the proper ideal must survive and either be alpha or be alpha inverse. And this is a serious problem. This contradicts the maximality. Or negative, say DJ. Because if J survives in one of these two ideals, then you've got a bigger pair. Say it survives in B alpha, now you've got a pair of B alpha and JB alpha, which is a strictly bigger ring than B, where the ideal I survives. Hence, B is a valuation. And so actually we get a little bit more from the proof of this theorem than I actually stated, the statement of the theorem. And what we get extra is the nice little result that if you have an overring that is maximal with respect to the property that I survives in, it has to be a valuation. Okay, any questions? So, and here's the big let R be equal to one. Um, and in proposal, would be great to show you this notation. Yeah, so this is the set of all omega in the quotient field such that E omega is 0 for some my E of X and Rx. Then R bar is the intersection R is the intersection Ball valuation. The runs through collection of all valuation of. Now, tell me that's not cool. I double dog agree, right? Because really, this seems really different, doesn't it? Right? This is a collection of roots of monic polynomials, right? It's not even clear. I mean, Grant probably explained to you why this is actually a subgroup. Why probably we can prove that thing with the matrix, with the determinant of the matrix thing that showed that sums and products of integral elements are integral. Right? But here, if you believe this theorem, it's also clear that the integral closure is a ring because it's an intersection of both. So any intersection of rings is a ring, right? And this is completely, it seems very weird, right? That all the integral elements are just sets in every valuation of it. That's clear at all. So let me give you kind of a little limit here. Family of opening bar. Domain. So take an integral domain and let Ri be a family of over rings. If each Ri is integrally closed, so is its intersection. So this is actually not very difficult to prove, but it's a useful observation. What lies ahead? Let's prove this. Let X let not anymore. Let X be in the quotient field of R and suppose X is empty over the intersection of I. That means X satisfies an equation like this: xn plus alpha n minus 1, xn minus 1, alpha 1x plus alpha 0 equals 0, with each alpha I in the intersection of I. But for all I, alpha I for all I, each alpha j is in Ri, because each of these coefficients is in the intersection of all these Ri's, and so in particular it's in each of these Ri's. So that observation means, so X is equal over each RI. But each RI is interval closed. So X is in each RI because they're all interval closed by assumption. So X is in intersection RI, and this does. So that intersection is in closed. And what do we also know? We know valuation rings are interval closed. That's a theorem we used earlier. That means that the right side of the equation is interval closed. That might help you in proving this, and we'll talk more about this. Don't forget, our final exam, so to speak, will take place Thursday. I do not intend to use the entire exam period, but I might use a little bit more than the regular period, depending on how the world moves us. Don't forget, I'm going to go to that seminar today at 11:15, so whenever it's over, probably 4 or 5. Math in tomorrow. Don't forget to do the evaluation and the assessment. And class next week. Any questions? All right. Well, you guys.